Hi, my name is Rohan Poddar, and today I'll be talking about counterfactual multi-agent reinforcement learning. This research was conducted with Tong Yeo and Dr. Suresh Sundaram in the School of Electrical and Computer Engineering at Purdue University. First, I'll be introducing the fields of reinforcement learning and multi-agent reinforcement learning. Next, I'll be covering the tools and algorithms used for this research, including the original counterfactual multi-agents or COMA paper. COMA is a multi-agent algorithm that tries to solve the multi-agent credit assignment problem. That is, how much did an individual agent's actions help the team as a whole? In our work, we extend COMA to competitive and mixed-sum multi-agent settings, off-policy learning, and continuous action spaces. Reinforcement learning, or RL, is the application of data-driven machine learning to optimal control. It deals with control of an agent, such as a chess player, a power management system, or a robot, in an environment. The agent interacts with the environment through an action AT based on its current observation OT. It receives its next observation OT plus 1, as well as a reward RT plus 1. The goal is to learn an optimal control policy pi that chooses actions AT, which maximize the total discounted expected reward across time. We also define the expected state value function vpi and action value function qpi. These correspond to the expected reward under policy pi, starting from state S and action A, respectively. Maximizing either of these value functions is equivalent to finding the optimal policy. At the optimal policy, the expected value of the advantage, or the difference between Q and V, is 0. Deep reinforcement learning introduces neural networks as powerful function approximators to RL. Deep Q networks, or DQNs, use neural networks to represent the Q function. DQNs can learn off policy, that is, from experiences generated by a different or older policy. Thus, they can store an experience in a replay buffer and learn from it later, even if the policy has been updated since then. However, they only work in discrete action spaces. Policy gradient methods use a neural network to represent the policy itself. They only work on policy and cannot use a replay buffer, but can be used in continuous action spaces. The most common type of policy gradient method is an actor-critic method. This uses neural networks for both pi and q, v, or a. We optimize pi using the value function and the value function using the environment. Deep deterministic policy gradients, or DDPG, combines ideas from DQNs and policy gradients to form an off-policy method that can learn in continuous action spaces. Soft actor critics extend actor-critic methods to off-policy learning by rewarding the actor for the entropy or randomness of the policy. DDPGs only work in continuous action spaces, but soft actor critics work in both discrete and continuous action spaces. Deep reinforcement learning has had many public successes in the past few years, such as DeepMind's AlphaGo and AlphaStar, OpenAI's OpenAI 5, and so on. But in many real scenarios, there are systems with multiple agents in an environment, learning and executing actions simultaneously. For example, the Purdue starships making delivery across campus. This gives rise to the field of multi-agent reinforcement learning, or MAR, which can further be divided into fully cooperative, fully competitive, or mixed scenarios. In centralized MAR, a centralized controller tells every agent what to do. In decentralized MAR, every agent learns and acts completely independently. Most MARL research is set in the framework of centralized training and decentralized execution, or CTD, where policies are trained centrally and executed independently. A naive type of MAL algorithm is just using deep RL algorithms, such as independent actor critics, for all agents. However, this has numerous drawbacks, including a lack of coordination or communications, high variance of updates, and loss of theoretical guarantees concerning convergence of the policy. Multi-agent deep deterministic policy gradients, or MEDDPG, is a well-known MAL algorithm in which each agent has an actor and a critic. The critic has access to the full state information from the environment and actions of all agents. It learns off policy and is applicable to all three scenarios. Counterfactual multi-agent policy gradients, or COMA, instead uses a single centralized critic with a counterfactual baseline to address the credit assignment problem. It uses a counterfactual advantage to calculate the policy gradient for each agent. The counterfactual advantage is the Q value minus the policy weighted sum of Q values for all possible actions for the given agent, holding the other agent's actions constant. This gives an estimate of how the agent's individual action benefited the team at any point in time. Unfortunately, COMA can only be applied to discrete action spaces due to the counterfactual baseline summing over all possible actions. Since it is an actor-critic method, it only works on policy. Also, the original COMA paper was aimed towards the fully cooperative StarCraft multi-agent challenged environments. Now, we discuss the tools used for our MARL research. We use the multi-agent particle environments, or MPE, from OpenAI as implemented in Petting Zoo. MPE is a set of 9 simple environments with all 3 types of scenarios, while Petting Zoo is a library for MARL environments similar to OpenAI Gym for single-agent RL. We implemented and tested our algorithms using RLlib, a library for large-scale distributed reinforcement learning developed by any scale. We used a local laptop for development and a remote cluster for experiments. We implemented COMA in RLlib and benchmarked it on all of the MPE environments. In the competitive and mixed environments, each team had its own individual critic, like a coach telling each player how to do better. We show results on the simple reference environment from Petting Zoo MPE. This is a fully cooperative environment with 2 agents and 3 landmarks. Each agent knows the other agent's target landmark. The optimal policy is for the agents to communicate each other's targets and move to them. Because DDPG and SAC cannot learn collaborative policies, both agents move to the median of the 3 targets since this is the best possible independent policy. COMA is also highly inefficient because it is an on-policy method. Thus, its performance is relatively slow compared to MADDPG. We extend COMA to off-policy reinforcement learning using the maximum entropy framework presented in Soft Actor Critic. Our experiments confirm that the new algorithm, which we call COMEX, performs comparably to MADDPG on simple reference, while COMA learns the optimal policy eventually, and DDPG and Soft Actor Critic do not learn it at all. In future work, we plan to extend COMA to continuous action spaces using a similar approach as the soft key learning and soft actor critic papers. In the soft key learning paper, they convert an integral over the action space into an off-policy expectation using importance sampling. Here, small q can be any arbitrary distribution over the action space, even a discrete one. In future work, in conclusion, we showed that COMA works in competitive and mixed-sum environments and with off-policy learning. In the future, we plan to extend all 3 of these improvements and scale them to large multi-agent scenarios. We would like to thank SORF for their support and funding. We also thank Jiajun Shen at Purdue and Justin Terry and Benjamin Black at the University of Maryland for the agent interface figures and their advice on Petting Zoo, RLlib, and MARL.